Assalamualaikum warahmatullahi wabarakatuh. Kali ini kita kembali membahas yaitu motor listrik. Kali ini saya mengambil dari yaitu Air Training Command United States Air Force dari Angkatan Udara. Saya tidak membuat video sendiri. Ini video jadul ya, akan tapi sangat bermanfaat buat kita. Kali ini kita akan membahas yaitu motor induksi. Oke.
An AC motor is used in this electric razor. AC motors also rotate huge radar antennas. Electric clocks, drills, mixers, electric fans. The list of commercial appliances that use AC motors is almost endless, and it's getting longer every day. More important to you is the use of AC motors in electronic equipment, like this blower motor that is used to remove heat in some radio or radar sets. Without these motors, the buildup of heat would damage the delicate electronic components within the equipment.
Oke, kita lihat bahwasanya banyak sekali kegunaan dari motor AC. Di antaranya tadi ada drill, ada macam-macam memutar antena sampai potong alat cukur dan lain sebagainya. Ini seperti ini adalah blower yang mendinginkan peralatan elektronik. Kalau blowernya mati, alat elektroniknya akan rusak. Oke.
The point is, since AC motors are so commonly used in almost every kind of work, it makes good sense for you to learn as much about them as you possibly can.
Ini macam-macam motor ya, motor AC motor.
There are many different types of AC motors. There are synchronous motors, repulsion motors, universal motors, and induction motors. Of these, the induction motor is probably the one most commonly used because of several reasons.
Okay.
Its simplicity of construction, its relative low cost, and its ruggedness.
Oke. Macam-macam jenis motor AC ya. Ada motor sinkron, ada motor macam-macam ya. Kita bisa lihat di sini. Ini adalah diantaranya macam-macam motor, jenis-jenis motor AC. Ya, ada sinkronus motor, ada AC komutator motor. Itu seperti yang dipakai motor bor ya, mesin bor itu pakai komutator untuk kekuatan yang besar ya. Cuma boros ini ya. Ini pun juga dibagi satu fase, repulsion motor, charge motor, kemudian ada yang disebut yaitu induction motor. Ada induksi, motor induksi satu fase, ada motor induksi 3 fase. Khusus motor induksi ini yang paling banyak digunakan karena konstruksinya sederhana dan murah. Ya. Oke, kita lanjutkan lagi.
For these reasons, you will see induction motors like this one that supply only a fraction of 1 horsepower. Others will vary in size according to the job they must do. So, in this lesson on AC motors, we'll concentrate our attention on the induction motor. Once you
Konsentrasi
understand
kita
this
kali ini
operation, it's a
bicara
simple matter
induksi
to understand the
motor.
operation of the other types. Now, to begin our examination of the induction motor, let's take a look at how it's put together, its physical construction. Oh, don't worry about your TBI guide for a while. We'll fill it out during the review, after we finish the discussion. Bob?
Oke, kita akan melihat secara fisik bagaimana motor induksi.
Okay. This is a typical induction motor, disassembled. Now, as we've said, it's very, very simple. We have the 2 end bells, the stator field windings, and the rotor.
Ya, konstruksinya sangat sederhana, yaitu 2 end bells ya, ada 2 tutup ya, 2 tutup, kemudian stator atau housing rumah motor ya, kemudian ada rotor. Cuma 3 macam saja. Oke.
Now, let's take a look at these end bells. The end bells are used to house the bearings or the mounting devices that hold the rotor shaft in place.
Nah, jadi end bells ini gunanya untuk rumah piring, untuk tempat poros dari motor induksi.
Now notice there are no brushes or complicated brush holding devices at all. Just simply hold the bearing. And also inside the housing, or inside the end bell, we would find the housing that contains the stator field winding.
Kumparan
Now notice the
stator.
simplicity of construction. We have the stator field windings, the iron core. Very, very rugged and very simple. Inside the stator field windings, the rotor.
Di dalamnya terdapat rotor.
All right, the rotor has no commutator, no slip rings, and no wire windings.
Nah, kita lihat rotornya sangat sederhana juga. Tidak ada komutator, tidak ada slip ring, tidak ada cincin belah, cincin putar, tidak ada. Dan tidak ada kumparan yang banyak. Cuma seperti ini saja. Okay?
It doesn't look at all like the rotor used in DC motors, does it?
Not at all.
Now this particular rotor design is called the squirrel cage rotor because it resembles the exercise cages used for pet squirrels.
Ya, biasa juga disebut sebagai sangkar bajing, motor sangkar bajing karena sederhananya. Okay?
Like the squirrel cage, the rotor is very simple to construct. Simplicity of construction, which of course leads to lower cost of manufacture, and a very rugged design, makes the induction motor a very popular one. There are no wires on the rotor to burn out, no brushes to wear, no commutator to get scratched or pitted. All in all, a pretty good motor.
Of course, it's not perfect for every application. It does have certain limitations. But even so, it's used quite extensively. Now, there are several types of induction motors, but they all operate on the same basic principle. The same basic principle which can be illustrated like this.
Oke, prinsip dasarnya akan digambarkan sebagaimana berikut.
Okay, what we have here is a cardboard disc, and on the disc it's mounted on a pivot, by the way, so that we can spin it, and we have two permanent magnets glued to the disc.
Oke, kita punya karton ya, karton disk dari karton, piringan karton yang dipasang poros tengahnya, kemudian ada dua magnet di sini.
Thus, if we spin the disc, we have a rotating magnetic field.
Ini akan menjadikan medan magnet yang
if we take another
berputar.
magnet, such as this compass needle, and put it on the pivot, in other words, so it's free to rotate, and we spin the cardboard disc, we have a rotating magnetic field. Now you'll notice that the compass needle picks up the rotation of the rotating magnetic field, tries to align with it. And this is an extremely important principle. Let me say that again. We have a rotating magnetic field, we have a compass needle. Look at it pick up the rotation of the rotating magnetic field. As it tries to align with the field, it begins to rotate.
Oke, kita lihat di sini ada medan magnet yang berputar. Tengah-tengahnya kita taruh jarum kompas ya atau magnet yang lain. Maka lama-kelamaan jarum kompas ini akan ikut berputar mengikuti medan magnet yang berputar. Okay.
Now this principle is the one that makes the AC motor operate.
Inilah
In the
prinsipnya
induction
motor
motor, the
AC.
moving or the rotating magnetic field is supplied by the stator field winding.
Right.
And the rotor follows this field movement because it becomes an electromagnet. In other words, when current is applied properly to these windings, a magnetic field is generated that rotates about the housing. Now,
Oke, jadi medan magnet yang berputar ini didapatkan dari stator, kumparan-kumparan stator di sini yang berpindah-pindah magnetnya seakan-akan berputar. Sedangkan magnet yang di tengah dibuat dari elektromagnet. Oke.
field windings do not move themselves, and this rotor is not a permanent magnet. But watch what happens when the rotor is placed inside the field winding.
And the power is applied.
The rotor rotates. Now, it's not physically connected to the field windings in any way, but it does rotate. Why? Simply because the field windings are providing a rotating magnetic field that induces a voltage into the rotor that causes current to flow, and the rotor becomes an electromagnet. And once it's magnetized, it's got to follow the rotating magnetic field, just like the compass needle did.
Oke. Jadi yang di luar sini stator dia karena berputar maka menginduksi. Ini semacam trafo ya. Ini primernya, ini sekundernya. Sehingga kumparan yang di dalam sini listriknya ikut mengalir. Karena ikut mengalir, akhirnya jadi magnet, elektromagnet di sini. Ini bukan magnet permanen, tapi jadi elektromagnet. Ikut karena ada induksi dari luar sini, medan magnet yang bergerak. Okay?
Now, Bob, we should point out that this rotor is not the correct size for this motor.
No, it's a little smaller than the one that belongs in here.
Well, we've used a smaller rotor to emphasize the fact that there is no physical connection between the rotor and the field winding. Actually, there are two major points to discuss in order to understand how the induction motor operates. First, we must have a rotating magnetic field produced by the stator winding. And second, we must cause the rotor to become an electromagnet. So let's first determine how we can produce a rotating magnetic field.
Okay, coming up.
Oke, kita akan membahas yang pertama adalah bagaimana medan magnet yang berputar. Kemudian yang kedua nanti bagaimana yang di tengah tadi bisa jadi elektromagnet. Oke, kita lanjutkan.
Now these four coils represent the stator windings of the induction motor. Actually, they're wound to act like solenoids for this demonstration. We made them out of a deflection yoke from an old television set. Of course, the stator windings in the induction motor are not made exactly like this, but the magnetic field produced is essentially the same. Now this switch on the bottom will allow us to apply certain voltages with certain polarities to these coils.
Oke, kita punya 4 kumparan, ya. Kemudian di sini ada saklar yang mengubah-ubah arus listrik di sini, jadi plus, jadi minus, dan seterusnya. Oke.
And on this chart, we'll show these polarities during each increment of time.
Oke, ini ada kartu yang menunjukkan grafik bagaimana posisi listrik yang ada di sini. Oke.
Now in the center of the coil, we've placed a permanent magnet with an arrow on it to show the direction of the magnetic field at any one time. Now,
Oke, di tengah sini ada magnet permanen yang dibuat bisa berputar. Nanti akan mengikuti magnet yang di luar. Oke.
this permanent magnet is simply glued to a ball bearing so that it can rotate freely. Now the object of this demonstration is to cause this arrow, this magnet, to rotate 360 degrees by causing the magnetic field produced by these coils to rotate 360 degrees.
Oke, bisa berputar
So that you can
360
understand
derajat.
exactly why this happens, let's take a look at the way these coils are wound and how the voltages will be applied. Now actually there are really only two coils.
Sebenarnya hanya 2 kumparan saja. Kumparan 1 sama kumparan 2 saja. Oke.
We'll call them L1 and L2. Now L1 was wound something like you see it. And then the core was cut in the middle and stretched apart. Now it's still one coil, but now it's got a gap in the middle.
Oke. Ini tengah-tengahnya cuma dipisah saja. Ya, sebenarnya masih satu kumparan, cuma ada renggang di tengah untuk tempat rotor tadi. Oke.
L2, the other coil, was constructed in the same way. Now L2 will supply a horizontal magnetic field, and L1 will supply a vertical magnetic field. So if we supply voltage to just L1, we'll of course cause a vertical magnetic field. And the field lines up like this.
Oke, kita lihat kalau di sini dikasih plus, maka arus listrik mengalir ke sana. Mengalir ke sana, kemudian ke sini, ini juga mengalir ke sana. Oke, kemudian ke ground sini. Oke.
Now this arrow, like the arrow on our trainer, points to the north pole of this magnetic field.
Oke, jadi sini jadi kutub utara, sini jadi kutub selatan. Maka di sini magnetnya akan tertarik karena kutub yang tidak sama akan saling tarik menarik ke sana. Kita ingat aturan tangan kanan, ya. Aturan tangan kanan. Nah, kita lihat di sini. Nah, kita ingat kalau satu kumparan semacam ini dialiri arus listrik, kalau arusnya mengalir ke sana sesuai dengan jari-jari tangan kanan kita, maka sebelah jempol di sini ini menunjukkan kutub utaranya. Jari-jari ini adalah arus listrik, kemudian jempol menunjukkan kutub utara. Oke. Nah, kita juga harus ingat kemarin bahwasanya kalau kawat dialiri arus listrik, arahnya searah dengan jempol, maka akan timbul medan magnet di sekitar kawat tadi yang arahnya sesuai dengan jari-jari yang lain. Oke. Jadi dengan aturan tangan kanan ini bisa dua, bisa untuk melihat medan magnet yang terjadi pada kawat beraliran, juga untuk menentukan kutub utara dari satu elektromagnet. Oke, ini kalau kita beranggapan bahwasanya listrik mengalir dari plus ke minus. Nah, sedangkan di video itu mereka menganggap bahwasanya listrik dari minus ke plus. Maka aturannya dibalik, pakai aturan tangan kiri. Sama, cuma aturannya pakai tangan kiri. Oke.
Right up here. And right here, Tom, we should point out that you can apply the left-hand rule and determine the magnetic polarity of these coils. We're not going to take the time to do it now, but it'd be a good idea for the students to do that, and they can actually prove that what we're saying is quite true.
Right, that's a good point. Another good point is, if we reverse the polarity on L1,
make this a negative, in other words.
Right, we'll, of course, reverse the direction of the magnetic field produced by L1. And the rotating magnet will again line up with this magnetic field. Now, the same thing, of course, applies to L2. With voltage applied only to L2, we'll produce a horizontal magnetic field.
Like that. There we go.
And if we reverse the polarity applied to L2,
we go from positive to negative again.
We'll, of course, reverse the direction of the magnetic field. Right. Now, from this, you should see that we can already produce 4 magnetic field directions, up, down, left, and right, simply by supplying the proper polarity of voltage to each coil. And we can also energize both coils at the same time and produce 4 more directions.
And pause there.
Now, by supplying both L1 and L2 with this polarity, L1 produces an up direction, L2 produces a left direction, so the two equal fields combine and move up and left at this angle.
Oke, saya pikir mudah dipahami sudah ya. Jadi kalau arusnya mengalir dari sini ke sini, maka ini ke atas. Kalau yang dari sini, maka di sini ke kiri. Kalau dua-duanya, maka dia akan di tengah di sini. Oke.
And of course, if we reverse the polarity on both coils, we would, of course, reverse the direction of the magnetic field.
We're going from positive to negative again. This.
Exactly opposite polarity, and we reverse the direction of the magnetic field, causing it to move down and to the right.
Right.
Well, that essentially is what we're going to do in this demonstration. Simply supply voltage with the proper polarity to cause a magnetic field to rotate 360 degrees in a clockwise direction.
Right.
Now, we could just as easily produce counterclockwise rotation by reversing the direction of the windings on L1 and L2, but we chose clockwise. All right, Bob, let's reset the demo to the time 0 position.
All set.
Now, at this position, the pointer indicates 0 degrees, pointing straight up.
Oke, kalau kita praktekkan ternyata sama seperti tadi. Di sini posisi seperti ini adalah 0 derajat. Nah, posisi 0 derajat. Oke.
From this, we know that only L1 has voltage applied to it.
Hanya L1 yang dialiri listrik, L2 tidak dialiri sama sekali.
The graph shows that the value of this voltage is a positive 10 volts. At this time, of course, L2 has no voltage applied.
Oke, di sini 10 volt L1 ya. Kemudian yang di sini 0 volt. Tidak ada.
All right, switch it to time 1.
There we go.
Now, at time 1, the pointer is indicating 45 degrees. Now, this tells us that both coils must now have voltage applied to them.
Oke, pada posisi kedua, di sini positif 7 volt, sini juga positif 7 volt. Yang L2 naik, L1-nya turun. Tepat di sini. Oke.
Now, the voltage on L1 has dropped to 7.07 volts. And the voltage on L2 now has risen to 7.07 volts. I switch it to time 2. At time 2, the pointer shows that only L2 now has voltage applied.
Sekarang hanya L2 saja yang dialiri listrik, L1 tidak dialiri. Oke.
It's at maximum positive in volts. L1 is now at 0 volts. At time 3, the pointer again indicates that both coils are energized.
Ya, pada posisi ketiga, maka L1 dibikin minus, min 7 volt. L1 ini minus, sehingga dia terbalik. Kemudian L2-nya positif 7 volt, sehingga mengarah ke sini.
The graph shows L2 at positive 7.07 volts and L1 now at negative 7.07 volts. Now notice that the polarity on L1 has been reversed. This was done to reverse the direction of the magnetic field produced by L1. It's now down instead of up. I think time 4 will prove this, Bob.
Sure will.
Now only L1 has voltage applied.
Oke, sekarang yang ada aliran listriknya cuma L1, tapi terbalik. Jadi minus di sini. L1 jadi minus 10 volt, L2 0, tidak ada arus. Oke.
Of course, it's negative 10 volts. Now see the difference between time 4 and time 0. At time 0, L1 was at max positive. The pointer showed that the magnetic field was moving up. However, at time 4, L1 is at max negative. The polarity is reversed, and the pointer shows that the magnetic field is also reversed. Okay, Bob, switch it to time 5. And once again, the pointer shows that both coils are energized. Now notice that we also have reversed the polarity of voltage applied to L2. Now, both coils are at a negative 7.07 volts.
Sekarang, kedua komparan dikasih negatif minus 7,07 volt. Sehingga arahnya ke sana. Oke.
At time 6, and only L2 has max negative applied. Now, L2's field has reversed as indicated by the pointer. L1 at this time has 0 volts applied. Now, at time 7, both coils energized. L2 at negative 7.07, L1 at positive 7.07.
Oke, pada posisi ini, sini positif, sini negatif. L2 ini negatif, L2 pasti negatif di sini. Sedangkan L1 pas positif di sini. Oke, demikian berulang. Kembali lagi ke sini lagi. Oke.
And at time 8 we're back at 0 degrees where we started. And our voltages and polarities are also at the same values we started with. L2 is at 0 volts. L1 is at max positive. So we have rotated the magnetic field 360 degrees. But we used DC voltages to do it. And this is supposed to be an AC motor. Well, look at the graph of the DC voltages that we used to produce one revolution of the magnetic field. Here are the voltages applied to L1. And here, the voltages applied to L2. Look familiar?
They sure do.
If we connect all the voltages applied to L1 and all the voltages applied to L2, we find that we have two AC voltages that are 90 degrees out of phase. Well, that's why we use 10 volts and 7.07 volts. Now, 10 volts is the peak voltage of these AC sine waves. When we divide the sine waves into 45-degree segments of time, we see that these points are exactly 7.07 volts. So using these values, we constructed a sine wave that moved through 360 degrees.
Oke, kita lihat di sini. Ini adalah seakan-akan dua gelombang dari listrik AC yang tertinggal di sini. Nah, di sini 45 derajat. Ini tertinggal seperti ini. Oke.
And then by applying these values to the trainer, we move the indicating arrow through 360 degrees. The important point for you to remember is that two out-of-phase AC voltages will cause the magnetic field to rotate just like the DC voltages. Only with AC applied to the coil, the rotation will be a lot smoother, and we won't need a mechanical switch. The voltage values and polarities will change automatically as the input AC changes.
Oke, di dalam listrik AC, polarity atau arah listrik berubah dengan sendirinya. Tidak usah pakai saklar mekanik seperti tadi. Oke.
Now another point is, one cycle of AC produces one revolution of the magnetic field. In the example that we just used.
Ya, satu siklus listrik AC menghasilkan putaran 360 derajat atau satu putaran penuh.
Now the actual speed of the magnetic field of an actual induction motor would of course depend on the design of the field windings, the number of pole pieces, and of course the frequency of the applied AC. Now these field windings have AC applied to them.
Not yet.
Huh?
Now they do.
Oh, you turn the power on.
Right. We've applied it.
I'll start over.
Okay.
These field windings have AC applied to them in the proper phase relationship. They are producing a rotating magnetic field,
Right.
which is easily proved when this
Well,
chunk of iron is dropped into the field.
proved, Tom, not really easily, because the magnetic field is attracting the rotor toward the
You
center.
say it's
Now
kind of
we've got
hard to get
it.
in?
Yeah, we've got it in there now, and if I let go of it,
It rotates.
right.
And obviously something must be causing it to rotate.
Mm-hmm.
And that something, the rotating magnetic field.
Right.
A rotating magnetic field. But how does this cause the rotor to become an electromagnet?
Well, you remember the requirements for induction?
I sure do. A magnetic field, conductor, and relative motion.
Oke, ini supaya terjadi induksi, maka yang pertama harus ada medan magnet. Yang kedua ada konduktor. Kemudian ada relative motion atau gerakan relatif. Nah, supaya apa? Supaya bolak-balik medan magnetnya supaya berubah di dalam konduktor sini. Kalau nggak berubah, ya nggak ada induksi. Oke.
All right. We've got a magnetic field here that's rotating about the field winding. I'm going to take the rotor out of there and prove that we have induction taking place.
Why don't you explain?
All right, I'm going to do that. This is a coil of wire. The ends of the wire are connected to a resistor that is connected to the leads on our PSM6. The object is, if we get current to flow in this loop, we'll have current flowing through this resistor, we'll get a voltage drop, and we'll read the voltage on the PSM6, okay?
Okay.
Oke, ini ada kumparan, yaitu induktor atau kawat kumparan. Oke. Kemudian di sini tadi ada induksi magnet. Ada apa? Magnet yang berputar, medan magnet berputar. Di sini ditambah resistor supaya apa? Bisa dibaca alat ukur ya. Supaya listriknya mengalir dari sini ke sini. Oke.
Alright, now I'm going to take the loop of wire and place it in the field winding. Now I want you to watch the meter on the PSM6 here. Let me apply the juice first. You may hear a little hum being picked up by the microphone because of this magnetic field. Now as I place this loop of wire into the field winding, like this,
You got something there.
see the PSM6 indicating a voltage value.
That's induced voltage, huh?
That's right. That's the induced voltage from this loop. And you can see that I take the loop out, it goes away, put the loop back in. I've got to get the loop all the way down in there. There you go. Now we have the rotating magnetic field inducing a voltage into the loop, which we're reading on the PSM6.
Oke, kita lihat dengan medan magnet yang berputar, dia menginduksi menginduksi dari kumparan ini sehingga timbul listrik, generator. Jadi generator listrik. Karena arah medan magnetnya berubah-ubah, memotong kawat, maka kawatnya akan beraliran arus listrik. Okay.
Now the important thing to realize here is that once we get current flowing in this loop, once we get a current flow in this loop of wire, we have a magnetic field established about the loop. Now this means that we'll exhibit a north pole on one side and a south pole on the other. Or in other words, we have magnetized the loop.
Maybe
Right?
an electromagnet.
An electromagnet, right. Now,
Oke, kalau ada arus yang mengalir di dalam ini, kumparan ini, berarti ada medan magnet. Medan magnetnya sesuai dengan aturan tangan kanan tadi, ke arah utara sama selatan. Oke, seakan-akan dijadikan elektromagnet ini. Oke.
actually, the rotor is the same thing, or almost the same thing. And a rotor is made in a very, very similar way. Instead of using windings of wire, however, we use conducting ring on this end, conducting ring on this end, and they're joined together by conducting bars, these little white lines. And the reason I say conducting, sometimes they're made of copper, sometimes aluminum. This one happens to be aluminum. Now, current, as the rotating field goes around this rotor, current is caused to flow in the rotor, which sets up a magnetic field, and the rotor develops a north and a south pole. Now, once we magnetize the rotor, it has got to follow the rotating magnetic field, as you've already seen, just like that.
Oke, kalau ada listrik yang berputar, jadi elektromagnet. Sehingga magnet di sini akan ikut medan magnet yang berputar, maka yang tengah ikut berputar juga.
Okay? That's it. The rotor follows the rotating magnetic field as soon as it becomes an electromagnet. Same thing that occurred with our little demo, the permanent magnets on the card with the compass needle.
You should point out, Bob, that the rotor also has a core made of...
Right. Now the rotor is a little different than the wire loop because it has an iron core, or a material that has a low magnetic reluctance. Now this, of course, concentrates the magnetic field and makes the rotor a stronger magnet. So the rotor turns following the rotation of the magnetic field.
But, Bob, how fast does the rotor turn?
Well, to answer that one, we've got to reconsider the requirements for induction. You remember the requirements?
I sure do. Magnetic field, a conductor, and relative motion. Now, this relative motion is between the magnetic field and the conductor. And, of course, if there's no relative motion, then there's no induction.
That's right.
Oke, kalau tidak ada perbedaan antara rotor, kecepatan putaran rotor dengan putaran magnet, maka tidak terjadi induksi karena tidak berubah kutubnya, maka tidak terjadi generator tadi, tidak terjadi pembangkitan listrik, maka jadi berhenti. Nah, kalau ada perbedaan putaran antara stator sama rotor, maka terjadi induksi. Maka syarat yang ketiga harus ada relative motion. Okay.
So we know from that then that the rotor cannot turn as fast as the magnetic field, because if they were both turning at the same speed, there would be no relative motion between them. No relative motion, no induction, no current flow in the rotor.
Oke, kalau rotornya bergerak putar sama persis dengan putaran medan magnet di sekitarnya, maka tidak terjadi induksi, tidak jadi magnet. Makanya hilang magnetnya di tengah. Maka tidak bisa mengikuti persis seperti putaran medan magnet di luarnya. Oke.
And of course, if we didn't have current flow in the rotor, there'd be no magnetic field, no magnetism in the rotor. The rotor would just be another chunk of iron. And we also know that it can't turn faster than the magnetic field, because the magnetic field is what causes the rotor to turn. That is, it's the driving force.
Oke, rotor juga tidak bisa berputar melebihi kecepatan putaran medan magnet dari stator, karena dia cuma ngikuti, tidak mungkin yang gerakkan itu kalah cepat dengan yang digerakkan. Oke.
So if the rotor can't turn faster than the magnetic field, or even at the same speed, the obvious conclusion is that the rotor must turn slower than the magnetic field, right?
Absolutely brilliant conclusion.
Good.
But tell me, Bob, how much slower?
Now, that depends on two things.
Oke, seberapa lambat? Jadi rotor perputarannya harus lebih lambat dari medan magnet di stator. Tapi seberapa lambat?
The amount of internal loading and the amount of external loading. Now, what do we mean by that? Internal loading refers to the drag or the load on the motor caused by weight and friction.
Oke, itu semua tergantung dari beban dalam sama beban luar. Oke, beban dalam gesekan pada rotor, udara, dan lain sebagainya. Oke.
You mean like it would be easier for a little guy like me to push a small light car than it would to push a big old heavy clunker like yours?
It'd be easier for anybody.
Especially me.
Right. The same thing is true of this rotor. That is, it takes a certain amount of energy to overcome its weight to cause this hunk of iron to turn. And, of course, the friction of the rotor shaft on the bearings adds to the internal load. And there's a little cooling fan built into the rotor, and that increases the internal load. Now, the external load refers to the job or the work that the rotor must do.
Oke, sedangkan beban luar adalah beban yang ditanggung kerjanya motor ini untuk menggerakkan apa. Oke.
They turn gears or operate pulleys or maybe turn a fan blade.
That you just happen to have with you.
Happen to have one in my pocket, right?
Very good.
Now, when we put this fan blade on the rotor, we have increased the load or the drag on the motor. And therefore, it's going to turn a little slower. In fact, I've got to give her a little start there to get it going. Now, it turns slower.
Now, before, the rotor was turning almost as fast as the magnetic field under no-load conditions.
Right.
Now it slows down a little. Well, it slows down a lot because it's got work to do. There's more drag on it.
Right. That's the way.
Mm-hmm. So the rotor does then turn slower than the magnetic field. I think we proved that point, Bob.
Right.
Now, the difference between magnetic field rotation speed and rotor rotation speed is called slippage.
Ya, perbedaan antara magnet yang berputar pada rotor sama stator, kecepatan putaran rotor dibandingkan dengan putaran medan magnet ini disebut slippage. Oke.
And the greater the load on the motor, the greater the slippage.
That's right. Now, since we put a load on the motor, this fan, in other words, we cause the rotor to turn slower. Well, how do we generate enough energy to keep that rotor turning?
That's a very good question, Bob, and I hope you've got a good answer.
Oh, we do. The rotor becomes an electromagnet, right?
Right.
But how strong an electromagnet is the rotor? How strong should it be? It should be just strong enough to do the job. In this case, to keep the fan blade turning.
Oke, seberapa kuat medan magnet di rotor?
The strength of the electromagnet is determined by the amount of current that flows through the conductors of the rotor. The more current, the stronger the magnet, and so therefore the current in the rotor is determined by induction.
I've heard that somewhere before.
Oke, jadi kekuatan medan magnet yang terjadi tergantung dari arus yang mengalir. Arus yang mengalir terjadi seberapa besar relative motionnya. Oke.
Well, we know that the magnetic field strength is at some fixed level, depending on the applied voltage. And we know the number of conductors in the rotor is also fixed. So the only variable factor that could affect the amount of induction is the relative motion between the magnetic field and the rotor. Is that right?
Exactly. So if we increase the relative motion, we increase the rate or the frequency at which the conductors are cut by the flux lines of the rotating field. The greater the frequency of cutting, the more the current in the rotor, and the stronger the magnet. Now, that's why the rotor can continue to turn the fan.
Oke, semakin cepat frekuensinya yang diberikan, maka semakin besar arus yang mengalir, maka semakin kuat rotornya.
Flow to the fan causes the rotor to slow down, just as I can do with my finger here. I can cause the rotor to turn slower. As it slows down, the slippage increases. and the frequency at which the conductors of the rotor are cut by the rotating flux lines increases. More current flows. The magnet becomes stronger and compensates for the increased load.
Oke, kalau ini dibebani, maka perbedaan slippage-nya itu akan semakin besar, sehingga gayanya akan semakin tinggi, semakin besar. Oke.
Now there's a limit to this.
I thought there would be.
For example, if I make the load on the motor too great, as I'm doing here with my fingers, it stops. But the magnetic field is still zipping around there, right?
Right, nothing slowed it down.
No. So the frequency of cutting has gone way up. Now from this, you might think that the current in the rotor, when I've got it stopped like this, has also gone way up. But that's not so.
Look at this. As the frequency of cutting, which is F in this formula, as the frequency of cutting goes up, XL, the inductive reactance of the rotor, also goes up or increases.
Oke, kita lihat di sini sifat dari kumparan. XL ini adalah hambatan yang terjadi, impedensi yang terjadi atau hambatan yang terjadi itu sama dengan 2πfL. Ingat, ini adalah rumus dari hambatan yang terjadi pada induktans atau pada kumparan. Oke, kita lihat kalau frekuensinya naik, maka hambatannya juga semakin besar. Kalau frekuensinya turun, maka hambatannya juga turun. Nah, kalau hambatan besar, berarti arusnya juga turun. Nah, jadi tadi kita lihat bahwasanya frekuensinya naik, maka kekuatannya naik. Apa betul? Arusnya tambah besar. Frekuensinya naik, oke, tambah besar. Tapi dibatasi dengan sifat XL, yaitu 2πfL ini, yang memperbesar hambatan di dalam rotor itu sendiri, sehingga arusnya pun juga semakin turun. Oke.
Now we know if the reactance of the rotor increases, then of course the current in the rotor is going to have to decrease.
Right. So at this high frequency of cutting, that is when I've got it stopped, I'm holding it stopped, the reactance of the rotor becomes large enough to limit the amount of current flowing in the rotor's conductor. So too great a load will stop the rotor by increasing its reactance to a point where the current decreases. And of course, as the current decreases, the strength of the electromagnetic field decreases, the motor can no longer do its job, and it stops. Now actually, trying to operate a motor with too great a load on it will result in damage to the motor. And of course, that's why motors are rated for different loads.
That's very logical.
Okay?
Now this curve, which is known as a torque curve, will give you some idea of the relationship between rotor rotation speed, magnetic field rotation speed, and the turning force or torque generated by the motor.
Oke, kita lihat di sini. Maka ada grafik karakteristik dari motor induksi tadi. Kalau RPM-nya tinggi, semakin tinggi, dia pun juga akan turun juga. Nah, kalau RPM-nya rendah, maka dia rendah juga. RPM-nya naik, naik. Tapi dibatasi dengan yaitu 2πfL tadi, sehingga hambatannya semakin tinggi. Sehingga di sini terjadi grafik penurunan daya. Nah, kalau sampai di sini, maka ini motor sudah tidak bisa ngangkat lagi. Dia ngeden-ngeden tok, panas, bisa merusak motor. Oke.
Now with no load on the motor, the speed of the rotor is almost equal to the speed of the magnetic field. It's not all that much holding it back. But as the load is increased, as when Bob put the fan blade on, the rotor begins to slow down. The rate of cutting increases and torque increases, compensating for the added load. But at this point now, torque is maximum. Now, if the load is increased any more, as when Bob held it with his fingers, the rotor, of course, must slow down. The frequency of cutting goes way up to the point where the inductive reactance becomes large enough now to start limiting the current flow in the rotor. The strength of the electromagnet decreases, torque decreases. The motor stops and begins to overheat. Now, if left in this condition, of course, the motor will be damaged.
Oke, kita lihat. Kalau di posisi ini kecepatan rotornya, maka begitu dikasih beban, bebannya besar, maka dia gayanya torsinya semakin tinggi. Semakin bebannya besar, torsinya semakin tinggi. Dia mampu menanggungnya sampai maksimum. Kalau sudah maksimum, maka dikasih beban lebih, maka dia akan turun putarannya. Turun di sini, semakin lama semakin turun, akhirnya motornya stop, berhenti di sini. Motor akan panas dan akan terbakar. Oke.
Now the point on this curve where the motor is designed to operate is just about here. Now this allows the load to change slightly without upsetting the stability of the motor.
Oke, maka kalau ngasih beban di titik ini, supaya apa? Kalau dia bebannya bertambah, dia torsinya semakin kuat. Nah, sehingga putarannya tambah tinggi lagi. Begitu tinggi lagi, turun torsinya, dia mundur lagi. Akhirnya naik turun di sini. Oke.
Right.
Baiklah, saya rasa cukup sekian mengenai motor induksi. Selebihnya silahkan dipelajari. Sumber-sumber lain banyak, silahkan dicari. Oke. Terima kasih atas perhatiannya. Mohon maaf segala kesalahan. Assalamualaikum warahmatullahi wabarakatuh.